Hi everyone, welcome to this video on the transformations of power functions. When I say power functions, what I'm referring to are basically polynomial equations, but today we're going to look at a special form of them, and I like to call this the stationary point form because we can read the coordinates of the stationary point directly from the equation. Okay. When I say stationary points, what I'm referring to are local minimum, local maximum, or stationary point of inflection. And so before we get into these questions, we need to have a bit of an idea of the different types of graphs that we can actually form. Up here I've got the y equals x to the power of 2n. Okay, and so x to the power of 2n is just x to an even power because any number multiplied by 2 will be even. So this is going to be equations like your quadratic equation, so x squared, or a quartic equation, x to the power of 4, or x to the power of 6, x to the power of 8, and so on. Now the thing that all these even powered graphs have in common is that they generally have a minimum turning point and pass through the origin, and they have this kind of parabola-like shape. Okay. Alternatively, we have this one here, the y equals x to the power of 2n plus 1. So when we do 2n plus 1, where we put any value of n in, it's going to come out to be, any integer value of n I should say, it's going to come out to be an odd number because 2 times a number makes it even, and then when we add 1 it makes it odd. So this is like your cubic equation, or x to the power of 5 or x to the power of 7. And when we have graphs like that, they tend to have a stationary point of inflection, and so they look a bit like this. Stationary point of inflection at the origin. So those are the two basic forms that we're going to work with. So it's really important to keep in mind that an even powered graph looks like a parabola and an odd powered graph looks like a cubic. So when we work through these questions here, sketch f of x equals negative 2 at the front of x plus 1 all cubed minus 4. The x plus 1 in the brackets there, that moves the graph 1 unit to the left, or as we say, 1 unit in the negative direction of the x-axis. The minus 4 on the end of the equation just here, that moves the graph down 4 units, or again 4 units in the negative direction of the y-axis. The 2 at the front is a dilation by a factor of 2 from the x-axis, and the negative right there is a reflection in the x-axis, so that just flips the graph upside down. And so I'm going to just draw that. I can do that because I know the basic form, so it's going to be 1 unit to the left and 4 units down. So that's my point of inflection there. I know it's a point of inflection because it's a cubic graph. So it's got to have this shape here. And then on top of that, I know that it's negative. It's been reflected in the x-axis. So rather than going the same way as the one up this top right hand corner does, the shape of it is going to be more like that. Okay, that's the negative cubic sort of shape. And so I just need to draw that now. Now before I go and actually do that, I should calculate x and y-intercepts because a good graph should have those features. So I'll just do that down here. Sorry about that. So the y-intercept, we'll do that first because that's going to be the nice one to calculate. So let x equal 0. That means f of 0 is given by negative 2 out the front of 1 cubed and then take away 4. So negative 2 times 1 cubed is negative 2, and then take away 4 makes negative 6. So that's going to be the y-intercept down there. And the x-intercept, let y equal 0, or f of x equals 0. So we're going to have 0 equals negative 2 at the front of x plus 1 cubed minus 4. I'm going to add 4 to both sides and then divide by negative 2. So I'll get negative 2 equals x plus 1 cubed. I can take the cube root of both sides. So the cube root of negative 2 is equal to x plus 1. Now just so you're aware, the cube root of negative 2 does exist in the real number set. Because we can multiply a negative number by a negative number and then by another negative number, and it works out to be negative. So it's only even roots that we can't do for negative numbers. And then I just need to subtract 1 from both sides. So x equals negative 1 plus the cube root of negative 2. cube root of negative 2, I'm going to guess, is about 1.25 or somewhere around there. So, negative 1 minus 1.25, it's going to be roughly negative 2.25. So there's negative 2, so I know it's going to be just a little to the left of that. And draw my other point here, and then I can sketch the graph with its point of inflection, so it goes like that and down this way as well, labeling the coordinates as well, so 0, negative 6, and negative 1, whoops, that's interesting, negative 1 plus the cube root of negative 2 comma 0. And there we have it. As for the second one, question B, g of x equals 5 times 2 minus x all to the power of 4. So again, we consider the transformations here. And this is a power of 4 graph, so it's going to have this sort of shape here. So a bit like a parabola. The negative in front of the x is a reflection in the y-axis. So that's going to basically turn the graph around horizontally, which doesn't actually affect the shape of this graph. It might affect the horizontal translation though. To make this question a little bit easier, I might write it as g of x equals 5 out the front of negative x plus 2 to the power of 4. So the thing is, normally this plus 2 would translate the graph 2 units to the left. But because it is reflected in the y-axis, it's now going to go 2 units to the right. So I'm just going to keep track of that down here. It's 2 units to the right, dilated by a factor of 5, so it's a bit steeper. Okay, I think I can sketch that now. So we go 1, 2 units to the right. That's going to be the x-intercept. Calculate the y-intercept. So we let x equal 0. And that means we get g of 0 equals 5 out the front of 2 to the power of 4. Now 2 to the power of 4 is going to be 16. 5 lots of 16 should be 80. So I'll just put another point up here, label it 0, 80, and then I'll sketch the graph. Luckily we don't have to have the same scale on both axes, but our scale does need to be consistent on each of the axes. So there's the graph. Smashed it. Alright, third question. H of x equals 3 times x minus 5 to the power of 17 minus 6. So first things first, it's a power of 17 graph, which is an odd power, which means it's going to be the cubic sort of shape. It's going to be translated 5 units to the right and 6 units down. So I'll just put 5 there, 6 can go down here. So just labeling that stationary point of inflection. And, well, it's not going to be particularly nice to calculate the y-intercept because we're going to have a negative 5 to the power of 17, which is going to be a huge negative number. So I might just sort of not worry about that one, but we can calculate the x-intercept without too much trouble. So let y equals 0. So that means 0 equals 3 times x take 5 to the power of 17 take 6. I'm just going to add 6 and divide by 3 on both sides. So 2 equals x take 5 to the power of 17. I'll take the 17th root of both sides. And that's just x plus 5. So then, taking 5 from both sides, we get x equals negative 5 plus 17th root of 2. Don't really know what the 17th root of 2 is, but I imagine it's somewhere pretty close to 1. So the x-intercept is negative 5 plus 1, roughly. So yeah, that's about as far as we'll sort of go with that one. Just give me a second. Sorry, I don't know why I just changed that to an x plus 5. That was a little bit silly. I was thinking, this just isn't making sense. So, try that again. We will take the 17th root of both sides, and then I need to add 5 to both sides, so I get x equals it's 5 plus the 17th root of 2, which is going to make it about 6. So that is much better. Okay, I'll label that point with its coordinates, which were 5 plus the 17th root of 2 and 0. And I know that's going to go like really, really steep there because it has to go down to a massive negative number and something like that. So that's the way that we can do these kind of questions. I'm going to leave the video here and see you next time.